guys? All right. So the way we get the D field, we start by talking about the conditions. If the radius rho, and this would be the radial distance rho here, from the center of the axis to this point of observation, if it's less than zero, less than A, and which is A equals, in this case, 4 centimeters, then you can make the case that the integral of d dot ds, now this is cylindrical symmetry, right, class? And what do we know the integral of d dot ds in cylindrical symmetry will be? It's just what? The surface area of a can, isn't it, class? What's that? Anybody? John, what's the outer surface area of a can of radius A? You remember? Can you guys not unmute yourself? I thought hey, Ben and Tyler, you're co-hosts. Can you unmute? Oh, maybe I can. Go ahead. Try it again, John.
So you said for height 1?
Yeah.
It would just be 2 pi a?
It would be 2 pi, right? And times the radial distance rho, right?
Right.
That's the perimeter, the outer perimeter, and then times the height of 1 times d rho. That's always going to be the case, right? Now, what does that equal to? It's all the charge that's inside, right? Inside that Gaussian surface. So if you think about it, just try to draw it out here. If I have a radius rho that's less than 4 centimeters, well, all the charge is outside there, isn't it? Correct? There's no charge in that can. All the charge is in the pipe, and I have to get to at least 4 centimeters before I start seeing that. Y'all follow me on that? So that means this is 0. All right, there's no charge inside if we're less than 4 centimeters. So if I have 0, I'll put it as 0 here, and I divide it by 2 pi rho, I still have 0, and that means d rho equals 0, frankly, for rho less than 4 centimeters. That's the first condition, the first possibility. Y'all see that? Now the second possibility is going to be when we get into the pipe between a radius of A and rho. Not A and B, all right? We're going to go from A to rho, but rho will be required to be less than B. Y'all follow me? So we're not going to get outside of the pipe, but we're going to start inside of the pipe, possibly inside of the pipe to a point rho, and I'll try to draw that. Now we have this. When we have, what is that thing there? I don't know why that appeared. We'll just work with it. All right, now when we have rho greater than A and less than B, all right, now we go ahead and we say the integral of d dot ds on this side, we're in cylindrical coordinates, will be equal to the charge inside, right? Well, the integral of d dot ds, remember that's the outer rim, it's the outer part of this can, right? Height of 1, radius rho, that will be equal to simply 2 pi rho d rho. That'll always be for cylindrical symmetry, okay? Always. Now we have to find the charge inside. Well, Q inside for this one is pretty interesting. It's pretty clear too. Pardon me. What I'm going to do is I have to put up a volumetric integral. So that's a triple integral. Now you put the volume charge density, but here, remember the volume charge density from 0 for row 0 to A is 0, correct, class? Right? So now we put the volume charge density in, which is going to be, I'll just call it rho V0. I'm not going to put the value in. It's a constant value, right? And when we put the differential volume here, it would be rho d phi d rho dz. Now, I'm going to talk about this. We're going to have a dz integration, just 0 to 1, right? We only go from 0 to 1 in height. our row integration doesn't start at 0. The reason it doesn't start at 0 is because then we would have to have a separate integration where we'd have rho v is 0 when rho is at 0 all the way to a. So we start the row integration at a. Are you with me? And we end at rho. And then we start the phi integration from 0 to where? Fowler, you want to answer that one? I'm trying to get participation. Can you unmute yourself, Fowler? I thought I made it so everybody can unmute themselves.
There we go.
Go ahead.
Is that for the d phi?
Yeah, where do you go from? Anybody want to help him? Haran, Yun, you want to tell us? You got to unmute yourself, Haran. I'm spending too much time on this. 0 to 2 pi is the answer, right? That's what I'm trying to get across. I do this, I interact, and it will help you. It really will. Now, I have this, so let's evaluate it. By the way, people make mistakes on this. And it's because they're bored, it's so easy. Well, dz from 0 to 1, right? The integral of dz is z from 0 to 1 is just 1. So we kind of ignore that one. When we go rho, we have rho d rho, right? That's going to be rho squared over 2, correct, class? And I'm going to bring the rho v 0 out right now. So it's going to be when I integrate d rho d rho, I get rho squared over 2 evaluated from a to rho. Technically, I should say this. You should make this a prime because you're not supposed to integrate anything in here that has a limit here. The two cannot have the same variable sign. So typically, they make that a prime variable. It's called a dummy variable because it goes away at the end. So we'll get rho squared, right, evaluated from a to rho. Do you agree with that, everybody? And then when I integrate d phi from 0 to 2 pi, I simply get 2 pi, right? So that means the charge inside will be equal to 2 pi rho v 0, and then it's going to be divided by 2, right? This is going to be rho squared over 2. Yeah, over 2, right? When you get rho prime, d rho prime, it's rho prime squared over 2 and evaluated from 0 to rho. And then you're going to get rho squared minus a squared. And a, of course, is 4 centimeters. So that's the charge inside, and it's equal to 2 pi rho d rho. It's equal to the integral of d dot ds. So now I can say that 2 pi rho d rho is equal to 2 pi over 2 rho v 0 times rho squared minus a squared. And you can see plainly that the first thing that happens is the 2 pi's cancel. And then I divide by rho. Can you all follow me on that? Now, I left it like this. What happens when rho itself is equal to a, this term goes to 0. So the d field starts at 0 just at a. And as you go up, when you hit, as you're coming through there and you hit b, finally would be b squared minus a squared over b would be the value when you're actually at the outer limit. Do you all agree with this, class? And you can put in the rho v 0 divided by 2 later, but you got to follow the method. How many understand that right now? You all good with this? Right. Now the final part is now we're going to be for rho greater than 5 centimeters or greater than the outer radius, correct? All right. So now we say for rho greater than b, which is equal to 5 centimeters. Now I'm going to keep writing this down, and I encourage you when you do these things to write these things down over and over again. It'll stay with you, and you'll feel very confident. I wish I know how to get rid of this untitled thing. Oh, that's why. And this thing's frozen. Oh, is there any way I can move it? Can't even move it. All right. So when we're here, now you still write down the integral of d dot ds over the closed surface is equal to the charge inside, Q inside, right? Inside that surface. This is now a radius of is past 5 centimeters, right? So now when we look at this, the integral of d dot ds will always be 2 pi rho d rho. Everybody understand that? But on the other side, what will the charge inside be? It's going to be a triple integral, right? And now when we take a look at that, it would be rho v 0. Then you put down the differential volume. And in cylindrical coordinates, what's the differential volume, people? Well, it's the differential lengths all multiplied. So it's rho d phi, then it's d rho, and it's dz. Correct, class? All right. Z goes from where to where? Anyone? Thank you. 0 to 1. All right. Phi. How about phi? Carlin. How about phi? I'm going to try to get everybody participate.
From 0 to 2 pi.
Thank you. And finally, John, where does rho go from?
Well, I know it ends at B.
Well, where does it start at? It has to start where there's charge, right? Where does it start at?
A to B.
Yeah, that's right. And there are no wrong answers, by the way. I mean, there are wrong answers, but no answers that are going to be considered bumbling. And there are really no dumb questions either. I learned a lesson a long time ago, working with the Navy on the aircraft carrier Eisenhower. There are no dumb questions. A person never is ridiculed. You do that, bombs go off, stuff like that. You want to always make sure that the student is able, and by the way, the professor is able to ask anything without ridicule. And I'll never laugh at you or say it's a dumb question, unless you're going to ask something about football or something. That's off topic. All right, now, y'all see when we do this, this is going to have a value, but it's going to be a constant. It never changes, because now we're going to talk about all the charge inside. So when we integrate, take care of this, what do we get? When we integrate dz, we get 1, right? Then when we integrate phi, we get 2 pi, correct? D phi integrated is 2 pi, correct? Everybody? Then when we integrate rho d rho, and I didn't prime it right now, but you know it would be rho squared over 2 and evaluated from A to B. So now I would have simply b squared minus a squared over 2, and there would be a rho v 0. You agree with that, everyone? And that's equal to 2 pi rho d rho. Now, admittedly, I went through this methodically, very slowly. So you see all the steps. I didn't have a picture in front of me all the time, but you had a reference picture. So I cancel the 2 pi, and then I divide this by rho. And that would be d rho. And you could put in the value for rho v 0, d rho, and this would be for rho greater than b, greater than 5 centimeters. Correct, everyone? Now, what I ask people to do all the time is plot these things. So if you're plotting them, right? In fact, let me put this camera over here. So if you're plotting these things, and this is typically what I do, I put row here, call that A, call that B, and I ask you to plot D row, magnitude of D row on the vertical axis here. All right, now what is it from 0 to A? Anybody?
Could you slide it up?
Oh, I'm sorry, thank you. What I do is put D row here, and I ask you to plot it from, say, 0 to maybe 2B, something like that. I give you a range. What is D from 0 to A?
It's 0.
It's 0. At A, it goes up, right? It starts going up, but doesn't go up. It's not a discontinuous jump. It does this. It slowly goes up, right? And it's going up at the rate rho squared minus a squared over rho. If you look at this, the first term here, if you take rho squared over rho, that's rho, and it's minus a over rho. What that is something that's slower than a straight line. It's going to slope a little. It's going to go like this. Follow me? Now, we can tell what this value is right here, and we can get it from either this equation or this equation. This equation would be fine if here, right at the end where you're at B, you put in B here, and then you have a squared, you have B squared minus a squared over B squared. You could say that this peak value would be equal to rho V0 over 2, and then it would be B squared minus a squared over B squared. That would be the peak value right here. Do you all see that? And then it would start falling off like this. And here, the falling off would be proportional to 1 over rho. And you understand that's a proportionality symbol, class? And if you look right here, you can see once I'm outside where the charge is, I mean, when I say that at a radius greater than where I would actually be in the presence of the charge. So when I'm outside where the charge is, you see how it falls off as 1 over rho. This is important, you see this. Now, if you think about an infinite line charge, doesn't the field, the D field, fall off as 1 over rho? And the E field, correct, class? And this is one thing you're supposed to glean from the things that you're studying. Once you're outside where the charge is that's creating the field, when you get outside, either radially in spherical coordinates or in cylindrical coordinates outside of rho, it's creating, then the field starts falling off as if it was just either a line charge or a point charge. And it would fall off as 1 over rho if you were in, if you had an infinite, a cylindrically symmetric system of charge, and it would fall off as 1 over r squared if you had a spherically symmetric charge distribution. You good with that? Any other questions? I'm going to pose one for you, and we'll work this together to see if you understand it. Are you with me? I don't know if this one is in the book, but before I get into some of the other concepts, I'll talk about divergence in a second. It's fairly straightforward in voltage. I want to make sure you understand this. So here's Friday's quiz, only it's not going to be for points. It's going to be something that challenges you. How many people do we have here, by the way? Can somebody tell me? I can't see it.
6.
7.
Just 6?
Yes, sir.
Oh, yeah, 6.
Y'all got that email, right? I wonder where the other group is. Sleeping in, no doubt. That, or maybe they didn't get it. I hope they got it. All right. Well, I'll just assume they did. Here's the problem. I'll sharpen up in a second. I'm going to have a spherical distribution of charge. All right. And I'm going to say I have rho v equal to r squared times rho v0 from r greater than a less than b, and rho v is 0 else. And I want you to find the D field everywhere. You all follow me? So I'm just calling it rho v 0 times r squared, and you can say it's coulombs per meter cubed between A and B. Now this is spherical coordinates. And then rho v equals 0 else. So I want you to first draw it. Try to draw it. I hope you can draw better than I can. It looks like this. It's basically that you have a spherical surface like this. No, forget that. Let's do it this way. Spherical surface here of some radius A and an outer radius B. And here's where all the charge is, right? With me? All right, how do you do it? Tyler, where's the first starting point when we're doing a problem like this? If I want, say this is radial distance R, and I want the charge, what do I do?
Well, the first thing we need to do is find Q enclosed in terms of d rho, right?
Well, my starting point is always say the integral, it's not d rho in this case, it's dr, would be what? It would be the integral of d dot ds is equal to the q inside, right?
Yes, sir.
All right, well, your first step would be from 0 to a, correct?
Yes, sir.
It would be, if for the first part would be for r, radial distance less than or equal to a. All right, now looking at that, what would the integral of d dot ds be for this one? We're in spherical coordinates. We'll do it one time, but this should be automatic with you. It's really the surface area of a sphere, right? Of radius r times d. But what would this be? This would be actually an integral, it'd be a double integral, and it would be dr ar dotted with the differential spherical surface. And that would be equal to r squared sine theta d theta, and then it would be d phi, correct?
Yes, sir.
It's a little tight right there, but you can see d theta d phi. Well, theta would go from 0 to pi, and phi would go from 0 to 2 pi, right? Remember me doing this one before?
Yes, sir.
All right, now, and it would be in the AR direction. I didn't show you that. So AR dot AR would be 1. Now, when we integrate d phi, we get phi from 0 to 2 pi is 2 pi. And then we'd have an r squared that comes out. And then when we take a look at this, the integral of sine theta d theta is minus cosine theta. Minus cosine theta evaluated between 0 and pi. I'd switch the limits and go from pi to 0 and make it a plus cosine theta, but it's really 1 plus 1 or 2. So it's times 2. Or it's really going to be, and then it would be times dr. This equation right here, the integral of d dot ds, would be equal to simply 4 pi r squared dr. And that is the exact same thing as taking the surface area of a sphere. And the surface area would be 4 pi r squared and multiplying it by dr. That's it. So that's on one side. And then on the other side, that's the integral of d dot ds. So we have 4 pi r squared dr. And that will be the same for every single condition. Doesn't matter if r is less than a, between a and b, or greater than b. That's equal to the charge inside. For the first region, r is less than a. How much charge is inside? Just go out there and put a sphere.
0.
Anybody? It's 0, right? It's pretty obvious. Just make a spherical surface of radius r, but it's less than a. The amount of charge is 0. So this one's straightforward. We know dr for that case is 0 for r less than a, greater than 0. Now the second case is the interesting one. For the second case, now I'm at r greater than a, less than b, correct? All right. The integral of d dot ds will be the same as it was prior, and that's 4 pi r squared dr. Do you agree with me? But what about the charge? Now we're going to do the integral of the charge density. So I'm going to put a triple integral, and I put the charge density, and my charge density was rho v 0 r squared. All right. And now it's time times the differential unit of volume in spherical coordinates. Does anybody remember that? Tyler?
R squared sine theta, d phi dz.
R squared times the sine of theta, d theta, dr, d, not dz, d phi, you mean, right? There is no, let me rewrite that. That's a little messy. Let me rewrite it over here. So we have 4 pi r squared times dr. And on this side, then I'm going to put the triple integral. And I have rho v 0, r squared. Then I have the differential volume, which is r squared sine of theta. Then it's d theta, d phi, and dr, right? I'll do it that way. Theta goes from where to where? Carlin, where does theta go from?
Um, 0 to 1.
Theta is the angle from the North Pole to the South Pole. It goes from 0 to pi.
0 to
Are you
pi.
with- Yeah, y'all, you know, find out the level of understanding people have. And I'm trying to help everybody. Y'all understand that? That goes from the North Pole, which is at 0, to the South Pole. The angle's measured, right? The radius vector to the z-axis. And I hope y'all understand what I'm talking about. Maybe a little side note here. When we take a look at the z-axis, and this is r, this is theta. So it goes from 0 all the way down here, and that would be when it's opened all the way, and that would be pi. Pi radians are 180 degrees. Everybody got that? So it goes, so theta goes from 0 to pi. Now, where does phi go, Fowler? You might as well leave him unmuted. I'm going to be calling on you.
Phi is from 0 to 2 pi.
Yeah. And finally, the radius, John.
From A to R.
Exactly, exactly. That's exactly right. Just to R, not to B. So it goes from A to R. Very good. Everybody understand why? Because there's no charge density at a radius less than A, right? It's 0. So it has to start at A, and it goes to R. Now this integration, I'm going to go ahead and say this is going to be 4 pi r squared dr. On this side, well, I take rho v 0 outside. Then I take the r squared outside. Oops, I can't. I got a dr integration here, and I got r to the 4th. I got rho v 0 here. Now I'm going to do the d phi integral, I mean the d theta integral. So I have sine theta d theta integrated minus cosine theta from 0 to pi. Now I've done that so many times, I know that's 2, right? I don't have to think about that. Y'all with me? So sine theta d theta from 0 to pi will be 2. Then I integrate d phi from 0 to 2 pi. And what's that going to give us? Obviously, just 2 pi, right?
Yeah.
Just 2 pi. Now we have r to the 5th dr. What happens there? R to the 6th over 6, right? Right? R to the 5th, right? You got R, I mean, we got, sorry, R to the 4th, pardon me. R to the 4th, dr is R to the 5th over 5. Agreed, class? Sorry about that. R to the, this is going to be R to the 5th over 5, and it's evaluated from A to R. Do you all agree with me?
Can you scoot the paper up just a bit?
Yeah, thank you. This is just the surface times dr. So it's 4 pi r squared dr, rho v 0, then we're going to have 4 pi here, and then we have r to the 5th over 5. Agreed? And then I'll put in the limits here, but I'm going to just show you that the 4 pi's cancel, right? That's going away. And then I can take the 1 over, I can take the rho v 0 over r squared. I can make it rho v 0 over r squared. And then when I do this, I'm going to have 1/5, and I have r to the 5th minus a to the 5th, right? Right there. And then I divide that by r squared. And that is D of R.
Professor, didn't you already divide by r squared over by
Oh,
the...
you're right. I did right here. Sorry. You're absolutely right. It's right there. But that's how you would do this, correct, class? Now that's the second one. And you'll notice it falls, if you take r squared into r to the fifth, you have r to the third here, right? And then you have r squared into a constant 1 over r squared. This thing's actually going to have a different kind of a plot, but we'll talk about that in a second. And I don't expect you to be exact with your plots, but you have to at least show the trend. Finally, for the third part, now I'm going to be for r greater than b, right? Get used to writing it down. The integral of d dot ds is equal to q inside. D dot ds will be what? Anybody? It doesn't matter. Anybody. Well, what is d dot ds? It's just d times the surface area. What's the surface area of the sphere, people?
4 pi r squared.
Thanks. 4 pi r squared times d of r is equal to the charge inside. I'm going to write this integration one more time. That's rho v 0, right? Times r squared. And now it's the differential surface, which is r squared sine of theta d phi dr. And now I go ahead and put the limits on. Theta here, I'm sorry, it's a little crunched up, but theta goes from where to where, people? We just talked about this.
0 to pi.
Right, 0 to pi. Phi goes from, throwing it out there.
0 to 2 pi.
Thank you. I'll start calling on people. And now, John, why don't you do this again? Where does R go from?
From,
Remember, we're outside, we're at greater than B.
so A to B.
Right. Right. Now we integrate over all the charge possible, right? You can't get any more. And what happens when we do this? Now I have 4 pi r squared on this side times d of r. And on this side, I have rho v 0. Then I'm going to have, when I integrate sine theta d theta, I get 2. When I integrate d phi from 0 to 2 pi, I get 2 pi. And then when I integrate r to the fourth dr, I get r to the fifth over 5, evaluated from a to b. So I have b to the fifth minus a to the fifth over 5. You agree? Everybody agree with me so far? Then I go ahead and get rid of the 4 pi first. Then I divide everything by r squared. And now I have d of r. And you should be able to see it like that. You agree with me? You'll notice that this particular d field falls off as 1 over r squared when I'm outside where the charge is. And it's just as if it was a point charge, right? Falling off in that trend is 1 over r squared. It's important everybody sees that. So now for plotting this, let's just take a look at what it would look like. And this is R here, and here's D of R. So what does it look like? If I'm moving too fast, yell at me. I don't think I am, but I might be. From 0 to A, anyone?
Zero.
Yeah, 0, thank you. Right. Now from A to B, it has that funny one. It's like r to the third minus 1 over r to r squared kind of deal, right? You can plot this out, but it's basically going to do this. It's going to come up like this, I believe. Then it's going to hit a peak here that we can calculate, and then it'll fall off as 1 over r squared. One thing I'm going to make note of, if you do not have any surfaces of charge density, but you have a volumetric charge density, the D field and the E field are continuous. You will not see this thing spike upward It'll start at 0. It will monotonically increase to a peak, and then it will fall. But that line is continuous. With me? Now, if you had a surface of charge, you know, like a spherical surface charge density, then it could go 0 and then spike and then come down. But it would be discontinuous. Here, it's a continuous trend. Y'all get that? And it's important to note that. How would we get this value? Well, what could we do? Couldn't we evaluate this one right at R equals B, right? Y'all see what I'm saying? I could evaluate this one or the prior equation at R equals B. Either one will get you the same thing. And this value would be rho V, right? It would be rho V0, this value. And then it would be at B, it would be B to the 5th minus A to the 5th over, and here it's going to be 5, and then this is going to be B to the 5th, right? And that would be the value of the peak. Now, I asked that kind of question, so I want to tell you, this is something I will ask you to evaluate. So you have to be focused on how to get that. Agreed, everyone? All right. Any other questions before we move on to the next topic of interest? All right. I'm assuming that you did the problems and you have a fair appreciation for Gauss's law, right? That's the integral form. The differential form I don't spend much time on. The differential form of Gauss's law says divergence of the D field is equal to rho V. So the divergence could be in cylindrical, spherical, or Cartesian coordinates. And for the record, if you look in the back of your books, do you all have your books there? If you look in the back of the books, this is the mathematical operation for divergence. It's on the very, if you open your back, y'all got your books there, class? Fowler, do you have yours? And Carlin, you got? Okay. Just get them out, turn to the very back of the book. I want to make sure everybody sees this. It's in the inside the cover, a part of it, and then on the last page, this is the divergence operator for these three, for the three coordinate systems we use. Now, I want to tell you one thing about divergence. It is a scalar. It is not a vector. So when you do a divergence operator, you will be operating on a vector but getting a scalar. Unlike the gradient that we'll talk about, the gradient is a scalar voltage, but it gives you a vector E field when you do it. And we'll talk about that later. So if I take a look at Wentworth's books, problems, does anybody have a problem they'd like to work that deals with the actual divergence form of Gauss's law? Well, for kicks, just for kicks, let's take a look at 339 in your book. I hope you've got your book there. This thing is not 204, page 204. It says determine the charge density of 0.111, and they give you the D field. So what do we need to do? They want this, right? Rho V0. And they want the divergence of, you're going to have to take the divergence of this. I want you to take a look at this. What is the divergence of that D field? The D is equal to 3AX plus 2 XY plus 8 X squared Y cubed AZ. And the units are coulombs per meter squared. So what's the divergence of D? You can look in the back of the book. Well, technically it would be what? The derivative of D of X with respect to X plus the derivative of D of Y with respect to Y plus the derivative of D of Z with respect to Z. Agreed? You can look in your book, but that comes down to three simple derivatives with respect to the vector sense, a derivative of like D of X with respect to X. So when we do this, well, what's the derivative? First of all, what is D of X? Anyone?
3.
3. What's the derivative of 3 with respect to x? Thank you. Isn't it 0? It's a constant. Yeah, thank you. Plus, now the derivative, first, what is dy? It's
2x.
this, isn't it?
Yeah.
That's dy. What's the derivative of that with respect to y? Say it.
2x.
Thank you. Finally, the derivative of dz, this is dz, correct?
Yeah.
With respect to z is what? And I hope I wrote that right.
It's
Yeah.
0.
It's 0, correct, class? Now, some students have a way of making problems difficult. They think, oh, there must be something that comes out of that. So I'll write something down and ask for partial correct. I tell you, people reason through things in ways that are bizarre because they're thinking about getting points and not getting the right answer. Focus on getting the right answer is what I encourage you to do. So when I take a look at this right here, I see it's simply 2x, right? Correct, class? And that would be coulombs per meter cubed. And that means if I wanted the actual volume charge density at 1, 1, 1, what would it be? Well, you need the x coordinate, which is 1, right? Right? And what would it be? It would just be 2 coulombs per meter cubed. That would be the first part. Correct, class? Y'all see that? Didn't I assign this problem? I didn't assign this problem? Okay. I'm sorry if I didn't. Oh, no, I thought I assigned 39. Wait
I
a
don't
second.
think I find any on divergence.
I'm going to take a look and find out. 39.
It's a problem 337.
Sorry. You're right. I didn't. I'll assign some divergence problems today. I thought I was assigned 39, but I think that was too much. So anyway, that would be the divergence operator used. Correct, class? Now, the second part is find the total flux through the surface and see how the surface is from, it's a cube, well, a cube with 0 greater than x less than 2 meters. What he's talking about is this. He says if you have, this is x, this is y, this is z, and they want a cube, it goes from 0 to 2 meters. So here's 2 meters, here would be 2 meters, and here would be 2 meters. So he wants a cube like this, where basically you're going from x, y, and z between 0 and 2. Y'all follow me? Now he should have said that. It's a cube basically defined between 0 and 2 for x, y, and z, but he didn't.
Can you just get the paper up?
Yeah, thank you, thank you. I'm sorry I didn't show you that. This is a cube, so this would be 2, this would be 2, and the height would be 2. Now, when he asks for the total flux, this is the thing you have to catch. The integral of d dot ds over a closed surface is equal to the charge inside, right? Correct? Now listen to me carefully. We could do this integration. We have a d field right here that's defined with an x component, a y component, and a z component. And we could do that integration over 6 surfaces. That's a fair amount of bookkeeping, right? The math is easy, but it's a fair amount of bookkeeping. Here's an easier way to do it. You see how we have the volume charge density as 2x? We have rho v in that region is simply 2x, right? Coulombs per meter cube. Well, if I integrate that volume charge density over that volume, I'd get the charge, wouldn't I? Right? And that would be easier. It would be one integration. Admittedly, it's a volumetric integral, but it'd be a lot easier. And let's do that right now. So now we want the charge inside this cube. And this is problem 339. I'm going to flip the page, all right? I'm running out of paper. So when we do that, we get this. Lo and behold, we get this. Q would be equal to the triple integral of the charge density, right? This would be the same thing as the flux, the integral of d dot ds, over the closed surface would be equal to 2x. Remember, that's the charge density we calculated, right, class, by taking the divergence. Agreed? And then it's the differential unit of volume in Cartesian coordinates. Ben, what is the differential unit of volume in Cartesian?
Is it X, Y, Z?
dx, dy, dz.
Yeah.
dx, dy, dz. All right, now the limits. Stay there, Ben. Where does x go from?
0 to 2.
0 to 2.
And y?
0 to 2.
And z.
0 to 2.
Everybody follow me? This is a trivial integration. Q here becomes equal to, and just think about it, take the 2 out in front. X dx is x squared over 2, right? I'll put it down. Evaluated from 0 to 2 times dy integrated is y from 0 to 2 is 2. dz integrated is z from 0 to 2 is 2. So now I have this. I can cancel those 2's, and I have 2 squared right here. I can cancel that one and that one, and just evaluate this at 2 is 2 squared times 2 squared. That's 4 times 4, right? Or 16. And does anybody have can you look at your answers for this one, anybody? I don't want to keep shutting down and opening screens. That's what it will be. Haran, do you have those answers, the solutions? I posted, I think, the solutions to chapter 3, didn't I? Or not?
Yeah, it says the answer is 16.
All right. So what I'm telling you is that would be an application of the divergence form to get the answer. We'd get rho v, in other words, and then you do a volumetric integral to get the actual integral of d dot ds instead of integrating that thing over 6 surfaces. That gets tedious, by the way. All right. Now I'm going to give you some more problems out of here with divergence, but I want to tell you one thing. Here, like in 431, when you're in spherical coordinates, you don't use spherical that much, or you haven't. You will be using spherical almost. It'll be something that you will use more than you will use cylindrical coordinates or Cartesian coordinates when we get into antennas and stuff, and that would be an EMAG too. But you'll become very familiar with this unit system and the actual differential volumes and differential lengths and things like that. But the divergence of this requires you to look at the divergence operator in spherical coordinates, and I want to make mention of this. That operation is given in the back of Wentworth's book, but there are a lot more things to consider. There's a 1 over r squared, then ddr of not just a of r, but of r squared of a of r. Then you have 1 over r sine theta dd theta of the theta component times a sine theta. You have to take the derivative of the multiplicative product of those. Then a 1 over r sine theta d phi, or d of a phi d theta, or d phi. And this takes more time, and you have to be attentive to detail. Now, when I give a problem related to this, there's virtually 0 partial credit if you don't execute that correctly. So what I'm telling you is you have to be very focused. You cannot be sloppy when you do divergence. Got it? I'm trying to warn you ahead of time, because in the real world, making a mistake like that costs a lot. There's some of the mistakes people can find, but doing something like that and getting the wrong value means everything else is absolutely corrupted. All right. Now we push into something called voltage. I had a couple of PowerPoints that I wanted to just reference before. So it'll take, one second. Give me one. I sent you that one already, I believe. Did I send you this one too? I don't remember. Did I send you 4 PowerPoints? No? All right, well, let me send you this one. And let me get one other one in there. I'm only going to reference these, and I'll do problems here. All right. Tell me when you get them, so you can open them up and write. You can literally see them. And I don't like PowerPoints, but in this case, I'll use them. You get them, guys? Anybody receive that email? John?
I got it.
All right. Now, you don't have to look at that. I'm giving this to you because I want you to be able to reference it. You can mark this up if you got a printer. Y'all have a printer, by the way, or not? If you got a printer at home, you can print these and mark them up. But this is what the thing is with electric potential. Really, I like to think of this as I always term it voltage, and it's really electrical pressure. It's something, if you know the voltage between 2 points, you can think of it as the electrical pressure that wants to force something to move from one point of high pressure to the lower pressure point. So just try to keep that in mind. So the way they start with voltage is to say that we know from physics the integral of F dot dl is really the work involved in pushing something. Really, it's the work that an outside force would do moving an object from A to B here. And it's a very simple, it's a simple thing. You know, right? F equals ma, that's force. And the integral of force over distance is work or energy, correct? Y'all remember that, right? Basic physics. Well, if we think about electromagnetics, then the force, or electrostatics, the force on a piece of charge is really QE. Remember that in like one of the earliest lectures, we talked about force on a charge is Q times E. Do y'all remember that? That's fundamental. Actually, the first law I put up there was Coulomb's law, and it was F equaled QE. And really, we did the force between 2 charge points. So now that's the electrical force on an object. So if we take a look at the force that the electric field, or the work the electric field does, moving a charge from point A to B, try to understand this. This is the work that the field does. This is the electric field. If you put a piece of charge in immersed in an area or volume with an electric field, and there was nothing else involved, in other words, no atmosphere, no frictional force, and it moved it from here to here, then the electric field itself would have done this much work. It's the electric field present in the environment. And it's the same thing as gravity would do this. If I have a pen at this height and I leave it go, then gravity literally dragged it down to here, and I could find the force on that by finding the mass times the acceleration of gravity and just integrating or multiplying it by the distance it fell. That would be the amount of energy that the field or gravity did. Now, if you look here at the next part, the actual work that a person would do pushing the charge from here to here, say that the electric field was resisting it, would be minus this. Does that make sense to everybody? If the field itself does positive work, then if I'm an external force, I do negative work. Y'all with me on this, class? It's just perspective, right? All right, so now the actual work that an external force would do, and it says here, moving the charge, in this case, it's in the opposite direction, would be this. Same magnitude, opposite sign. Then the trick is this. If you want to know the work that an outside force does in moving a charged particle through an electric field, you simply take, or you would simply take minus Q times the integral of E dot dl from A to B. That's the definition. But we don't like leaving that charge there because we want it for an arbitrary charge. So we divide out the charge and we say that the work done from an outside force pushing on a charge divided by the value of the charge is called the voltage between B and A, and it's minus E dot dl. Now I'm going to go ahead and not just reference PowerPoints. Now I'm going to take you to the overhead and I want to show you some things. Y'all with me? This is the second time you saw voltage at least, right? You saw it in physics. You may have seen it in high school physics too. So let me shut that down. Let me get this back up. Now, knowing that, please make sure you write this down and go through that proof. I mean, how many remember that from physics? You've seen that, right? Your physics instructor made it a point to talk about the work that the field does and the work that the force would do. So now we take a look at the definition of voltage, and it's a voltage from B to A is actually VB minus VA. This is voltage. And that's equal to minus the integral of E dot dl. And E dot dl. And here it's going to go from A to B. And let me tell you where it is in Whitmore's book. It's formula 368, and it's on page 168. Are you with me? Now that's the voltage that's measurable that we use, and it's really the electrical pressure between some points. So the best thing to do is see this in action, calculate the voltage between 2 points. And one other thing I'm going to tell you, if you have a voltage meter, it's like putting the positive probe of the voltage meter at VB, the point where B is, and the negative part of the meter where A is. All right, so you can get, you've used voltmeters, right? You've measured voltages, haven't you, class? That'll give you an appreciation for exactly what I'm talking about. So let's do some classic problems. If I have a line charge, can you hang with me for a second? We had some technical difficulties, so give me a few minutes to make up for it. If we have a line charge, rho L, and put it on the z-axis, all right? And I want the voltage between 2 points. I want the voltage between point A, or I'll call it right here, A, and just say A is at radius rho. I mean, it's basically a radial distance rho, and point B. And B is also distance rho away. So really, I'll say I want VAB. All right, that's what I'm after. Now, I'm sorry that this isn't showing, but I really want the voltage from A to B. So A here, I've reversed this order. Maybe I better do it the other way. Let me go from VB to A, because that way it'll be consistent with what you have right there. That's technically the integral from A to B with a minus sign of E dot dl. Do y'all agree with that? That's the definition, isn't it? All right. So what is the E field from this line charge? If it's an infinite line charge, if I come out a distance rho away, what is the E field? Anybody? Anyone? Well, do y'all remember doing this? It's rho L, right, over 2 pi epsilon naught rho in the A rho direction, correct, class? Do y'all remember that's the E field from a line charge, an infinite line charge? We know what it is. Now we need the differential length. So the differential length in cylindrical coordinates, and you can write the whole thing out, but you're going to see only one term is of importance. Does anybody remember this? You do? Okay, good. What is it, Tyler? Differential length.
I remember the E field. I'm not sure what the differential length
Oh,
is.
all right. Well, the differential length, and didn't I post this stuff on OneNote for you guys? Don't you have that available to you? Y'all see the extra stuff I posted up there for differential lengths and spherical and Cartesian? Anybody? You know, you did see. All right. So what is it going to be? It's going to be d rho, right? A rho plus rho d phi a phi, right? Right? Plus dz az, correct? You can just look on that supplement that I posted on OneNote, but that's the differential length. Now, you'll notice when I take this differential length and I dot it with this E field, because we need E dot dl, right? Inside the integration, correct, class? That goes inside the integral. You'll notice that only the A rho dot product survives. These two go to 0 when we do the dot product, right? The dot product of the E field is only in the rho direction. Dot A rho is 1, but the dot product of A rho A phi is 0, and the dot product of A rho AZ is 0. So the integral of E dot dl, I'll make it down here when I put V BA is equal to minus the integral of E dot dl will only be equal to rho L over 2 pi epsilon naught rho, and then it would be just d rho. There is no d phi or dz. And the integration goes from A to B, right? It always goes from the lower limit to the upper limit. Now, when you do this integration, what do you end up with? Anybody? Well, you get rho L over 2 pi epsilon naught, right? And then what's the integral of 1 over rho, d rho? Anybody? What's the integral of 1 over x dx? Anybody?
Natural log of rho.
And so it'd be the natural log, and it would be the upper, which would be b over a, and there would be a minus sign. Now that's how you get the voltage between those 2 points. So depending if b is greater than a, this could be a positive or a negative voltage. I'll tell you one trick. If you have the log of x, that's equal to minus the log of 1 over x. So if you want to, you can invert a and b and get rid of that negative sign. Y'all follow me on that? A lot of times I do that right off the bat. I'll just get rid of that negative, make it the log of a over b. And that's really how you get the voltage between 2 points, or the electrical pressure. Last thing I'm going to make a point of, and I know I'm 5 minutes over, but we've had some problems today. When you think about voltage, I want you to think about this. Just take a piece of, let me get a different sheet of paper. Put a piece of positive charge anywhere. All right, doesn't matter how much, Q. Well, the E field points radially away from this charge, doesn't it? At any given distance, you know that the E field's pointing radially away from that charge, right? Now, here's the deal. The closer you get to the charge, the larger the voltage is. That should make sense. That's positive charge. The closer you get, the larger the voltage. So if you're measuring the voltage, V, call it AB, or I think he uses VBA, and you have a radius B here and a radius A here, where A is much further away, then think of putting a positive lead there of a meter and the negative lead there. This is the way I always do it when I teach in a real classroom. I say, you know what a voltmeter looks like? If you put a positive probe there and the negative probe here. Well, because this is at a range that's closer to the charge creating the electric field that would result in a voltage, this will have a positive voltage value. Now, if I reverse those leads, I'd have a negative. Y'all with me on that? And you know, you have a good sense for positive versus negative, right? In terms of batteries and things like that. So that's sort of the way I do this. I try to give you some insight. The closer you are to a charge, the higher the voltage is. It can be a line charge, it can be a point charge, it can be a surface of charge. We'll talk more about this next time. Does anybody have any final questions or comments? Now, I didn't get to voting on the test, and the reason partially is that we don't have our full class here. I'm only seeing what do we got here? 2, 4, 6 out of what, 12 or 14 people here. And I'm not sure what happened, if they're all playing hooky or what. But on Monday, would somebody remind me, matter of fact, all of you remind me to vote on the test, okay? Can we, talk among yourself, or would you rather do it this way? Would you rather give me an answer when you want your first test, and you can do a poll? I mean, you're all communicating with each other, aren't you? I mean,
Around what time period are you thinking, like?
well, not this coming up week, but it can be any time after this coming up week, whenever you want. And I'll let you guys can chat and come up with the time you want it, and then just give that to me. Tell you what, Tyler, can you be responsible for creating a poll and polling everybody, or who? You guys?
Yeah, we can do that.
If you could do that and give that answer to me on Monday, I'd appreciate it. All right?
Yes, sir.
You can communicate with everybody.
Yes, sir.
All right. Sound fair? What I'm giving you is the option to create the day of your test so that you don't have an assignment or another test that same day. Try to give yourself as much leeway. I will say one thing, and if you've had me before, you know I say this. On average, over the last 30 years of teaching, tests on Monday have higher average scores, I believe. And probably because you have the weekend to study and you're more rested. Tests on Friday usually have the lowest. Simply because people on Friday, they've got so many things to do, like on Thursdays and stuff like this. They usually don't have enough time to commit, and they're pretty burned out. So that's my advice. If you get a chance to choose between a Friday and a Monday, I would go Monday. It always seems to work out better. Okay. Any other thing in news for the good of the group? Any information about stores or bars or closing or anything like that?
Next week, do you have any plans for the mini-master finals that are going on?
Is anybody here taking? I can't ask the whole class right now, but because we're missing some. But is anybody here taking a mini-master course in the fall, last 5 weeks?
I'm taking one.
I mean, are you taking one now? Excuse me.
No.
If you're taking one now, then they have finals coming up Friday, right?
Right. I know other classes were not having class on Wednesday to Friday.
Well, I think, I'm not sure about Wednesday, but I can't, if there's anybody taking final exams on Wednesday and Friday, I can't require them to be in this class. All right. I mean, that's just the way it is, but I don't know who is and who isn't taking a mini-master right now. And it would be wait a second, there is no mini-master. So that would just be the first day of class? Or what is it?
It's the finals are next week, I think.
Oh, there is a 5-week mini-master, but it's just Zoom. Is that right? Okay. Is anybody here taking the 5-week first mini-master? If nobody is, we can have class those days. It'll benefit you. But if somebody is, then I have to excuse them. I'd still like to have class, because that way you're not going to get jammed up taking a whole bunch of topics and shoehorning them.
Mm-hmm. Yeah, I was just asking because other teachers were doing that. That's fine though.
Well, they can do that, but
mm-hmm.
You get yourself in a pickle when you got a course like this where I've got to cover 5 chapters, and right now we're in chapter 3, and I got I'm not even done with chapter 3. I've got 2 more chapters to cover, and the toughest one is magnetostatics, and that's coming up.
Yeah, I'm fine with that. I was just checking.
All right. I mean, I'll check with my department chair. If I have to cancel them, I will, but I don't think I have to. Unless I'm forced to do so, I plan on class. And one other thing too, please make sure you look at your schedules when your exams are, when your projects are due, when any of that, and try to schedule this as best you can on a day when you've got the least going on, or at least the least things due that day. Okay, that's my advice. You've been around the block. You know how to do this. Can you get that to me on Monday, Tyler?